I want to continue today talking about analysis of algorithms, and I'll quickly review the definition of what it means for something to be big O of some function as n goes to infinity. And then I want to talk a little bit about the algebra of big O notation, and then I'll finish with an analysis of the bubble sort algorithm and then the insertion sort algorithm that we're using in Huffman. So just by way of review, we say that if, let's see here, let's say f is a function of n. In the natural numbers. And for all, let's say there exists a capital N in the natural numbers, such that and a constant, a positive constant. Such that no, C is a real number.
Very real analysis by.
Yes.
I like it.
So, and I should say f and g are functions of n.
Oh, there exists.
Yes. So, and there exists a capital N in the natural numbers and a positive constant c such that this is true for all n, then f is said to be big O of g. And we saw an example last time where we let f equal 3n squared plus 2n minus 4, and we actually showed that f was big O of n squared. And all of these, you tack on this sort of perfunctory statement as n goes to infinity, as n goes to infinity, because in fact there is a big O notation. I'm mostly just dealing with natural numbers, but there's a big O notation for continuous variables x, and you can say that f is big O of g as x goes to a, for example. So this is a very specific situation where I'm just interested in n going to infinity through the integers, and this is consistent with computation where problems are usually of size n, and what we're interested in is how do these problems scale with n, how terribly do they grow as n grows. So last time we showed that f was actually big O of n squared as n goes to infinity, and this is typical. We're mostly interested in analysis of algorithms. We're mostly interested in big O of n to the p. And if p is 1 or if p is 0, then we say this is a constant. We say constant time. And that means that the algorithm takes the same amount of time no matter how big the problem is. If p is 1, then we say linear time. P equals 2 is quadratic time. And then after that, there are no real names for it. There are a couple of other interesting benchmarks. We say that f is big O of log n, and that's logarithmic time. And logarithmic time is, if you list these things in ascending growth order, we'll say that big O of 1 is sort of the slowest growing, and then the next slowest growing is big O of log n. And then in the examples that I've shown here, the next slowest growing would be big O of n, and then big O of n squared. Of course, there are things that you can put in between these guys. For example, between n and n squared, what's something that would maybe fit in between these two guys?
3 halves.
Yeah, you could do big O of n to the 3 halves, or you could also put in big O of n log n. And those are all also common things that you'll see in analysis of algorithms. Log n is really slowly growing. N squared's really quickly growing. You will also see things like big O of 2 to the n, which is a rapidly growing, exponentially growing algorithm with respect to n, and various combinations of these guys. So yes, fractional exponents are fine. N to the 3 halves is fine, and that's somewhere between n and n squared, n log n. Really, really slow algorithms, every once in a while you see this. That's a really slowly growing algorithm, but not constant. All right, let's look at.
It's actually bigger than log n, or smaller than log n?
It's smaller than log n. It's between O1 and O log n. Yes. So let's look a little bit at the algebra of big O. This is not a complete discussion of the algebra of big O, but it's kind of what we need in this class. First of all, we'll say that if f is a constant, then f is big O of 1. Yes?
So in order to show that the log n is of a higher order than the constant, you'd have to basically show that you can multiply it by a constant and it will always be, when you do that, it will always be bigger than.
There are a few different ways of doing it. You could also
Because what's confusing me is because isn't log of 1 0?
Sure. What saves me is this guy, this little caveat up here,
And then goes to infinity?
that there's a capital N,
Oh.
so it's way out there at the end.
Oh, okay, it's just like secant.
Exactly. And that's why that's there, because we really don't care what happens for small n's, for the first few n's. What we care about is sort of the long-term large n behavior. And so all the noisiness that might happen down below, where maybe this algorithm's a little bit faster for n equals 13, and then a little bit slower for n equals 22, all that stuff gets wiped out as you go out to infinity. So we'll say if f is a constant, then f is big O of 1. And that makes sense, because we take the absolute value of the constant. That's certainly less than or equal to k times the absolute value of 1, right? And that's true for all n in the natural numbers. So the constant c is just k, and the capital N is just 1 in this example. And you do see big O of 1. Yes?
Just a question about probably trivial technicalities. In the definition, did you have a strictly greater than or a...
I don't remember, but I would be comfortable. I would consider it a friendly amendment if we had greater than or equal to.
Okay.
Yes.
Okay.
So that's fine.
But it's not a problem. You could just make it k plus 1. And you
Yeah. All right. So here's a little bit. If f1 is big O of g of 1, and F2 is big O of G of 2, then F1 times F2 is big O of G1 times G2. Why is this convenient? Before I prove this, so if I have an algorithm F1 that's big O of n, and I have another one that's big O of n cubed, or n squared, say, then I can really quickly just say F1 times F2 is big O of n cubed without doing any work, once I prove this theorem. Do you see how to prove this theorem? Right? We can take this statement, we assume that statement, then we know that there exists an N1 and a C1, so that the absolute value of F1 is less than some constant, this constant C1 times G1 for all n bigger than or equal to N1. Right? And I can do the same thing for the second function, N2 C2, such that F2 less than or equal to C2 G2 and bigger than or equal to N2. And how do I finish this off? I can multiply those two inequalities together because they're inequalities of positive numbers, so I don't have to worry about any kind of sort of reversal. So I can multiply these two guys, multiply the left side, multiply the right side, and what I get is F1, F2 less than or equal to C1, C2, G1, G2. For what values of n is this inequality true?
When n is greater than n1 and greater than n2.
The maximum,
yeah.
Right? So when for n greater than the maximum of n1, n2. And of course that's some other number, n3, say.
Wait, no, it's not.
Sorry?
Max of n1 and 2 is either n1 or n2.
Yeah, but I'll just call it n3 since I can't call it n1 or n2. Right? Okay. So clearly n3 is, okay, not some other number. I misspoke. Yes. n3 is one of n1 or n2. All right. So we now have the existence of this natural number, capital N, in this case n3. We have the existence of the constant c, which is just the product of the two constants c1 and c2. Now we have satisfied the definition of big O, and so we can say F1 times F2 is big O of G1 times G2. Right? Another example, we can take a function f that's big O of, say, n squared, and we can say something very quickly about a constant times f. What's the constant times f? What's the big O? The big O of n squared.
Just multiply the original constant.
Right, or we can, or if you want to get really pedantic about it, you can say big O of 1 times big O of n squared. Right, and then, but yes, same thing. Let's talk about addition. So under the same assumptions as above, we can conclude that F1 plus F2 is big O of absolute value G1 plus absolute value G2. And you can probably guess how that's going to work. I've got the condition F1, absolute value of F1 is less than or equal to C1, G1, and that's for n bigger than or equal to, say, N1. And I also have F2 less than or equal to C2, G2, and that's for n bigger than or equal to N2. Where do I go from here? F1, F.
Show the name. Yeah. On the one day if you do math instead of.
That's what I told him.
I got lucky.
Yeah.
So am I right in saying these will be just like the proofs in real analysis about sequences improving?
Certainly similar, yes. We're not quite there yet.
Oh, triangle inequality? Yeah.
So we do have some triangle inequality to deal with. Where triangle inequality? Well, I just kind of gave it away. So F1, F2, right? That's less than. So applying the triangle inequality sort of in the other direction. But you begin to see why we're kind of stuck with this thing up here. It's not just big O of G1 plus G2. It's big O of absolute G1 plus absolute G2. But how do we get there? What's the constant that I need to use on the right-hand side? Max C1, C2. So I can say this guy is less than or equal to, say, C3, absolute G1 plus absolute G2. And that's where C3 is equal to the max of C1, C2, right? And now I'm there. Now I'm there. Why is that? Why am I stuck with those absolute values? What might happen if I didn't have the absolute values in there?
Negative 5t, 5t.
Yeah, I might have G1 might be negative n squared and G2 might be n squared. It would be kind of weird, but that might happen, and you'd get cancellation. And it's certainly not the case that F1 plus F2 would then satisfy that inequality. So absolute values avoid cancellation. Any questions about that before I go on and start analyzing bubble sort? That's not by any stretch the extent of the algebra of big O. There's also division, right? What happens when you divide F1 by F2, etc. Maybe we'll talk about that, but I wanted to get into some actual analysis of algorithms here. So to that end, let's analyze the bubble sort. Not the greatest sorting algorithm on the planet, but what the heck, got to start somewhere. Let me remind you what bubble sort looks like. For I equal 0, I less than n minus 1, I plus plus. For j equals 0, j less than n minus 1, j plus plus. And it's a pretty simple algorithm. We'll do an ascending sort if a j is greater than a j plus 1, then we're going to swap them. And that's it. So you guys have seen this possibly before. You have this outer loop. I starts at 0, and then you go to the inner loop, and j goes from 0 up to n minus 2. And let's look at j equals 0. For j equals 0, you have a0 greater than a1, and then a1 greater than a2, a2 greater than a3, all the way down. And we have to stop j. What's the upper limit of j in this loop? What's the highest value of j? n minus 2. And why do we stop at n minus 2? Well, we have a n minus 2 and then a n minus 1, and that's as far as I can go in that array, right? So I do have to be careful about that. Now, what happens for, say, I equals 0 for each pass of the outer loop? for each pass of the outer loop, the largest element in the array gets put into its proper position. The next largest one gets put into its proper position. So each pass in the I loop puts an element in its correct position. So how many times do I have to run this thing to get all of the elements in their correct position? N minus 1. Why not n? There are n elements.
Because if you put the top n minus 1 highest elements in their proper position,
then the last one has to be in its proper position, right? So every pass through gets one more element in its correct position. I get n minus 1 of them in their correct positions, and clearly the one that I haven't dealt with is in its correct position. So that's why the outer loop goes to n minus 1. Let's analyze this thing. Let's do a runtime analysis. So the runtime analysis, typically you work in nested loops. You work from the inside out. So I want to look at the inner loop, the J loop. How much work does one pass of the J loop take? Is it constant time? Does it depend on n in any way? So does one pass of the J loop depend on n in any way?
hopefully not. Is it useful at all?
Yes. So the answer is no. So the section inside the J loop we say is big O of 1. Now we're not going to use that. We're going to use an actual constant. We'll say that it takes time t to do one loop of J, one step of J. How many times did we run the J loop? N minus 1 times. Like that, right? Is that right, or n minus 2? 0 to n minus 2, sorry. You don't need to put this summation sign in there, but I'm just sort of giving you some tools that'll work in general. That's the same as n minus 1 times t. Right? How many times did I do this thing? I did it n minus 1 times, and each time through took t amount of time.
So t is evaluating the if statement?
T is just whatever time it takes to do that if statement and the swap.
Granted, those are different depending on the outcome of the if statement.
Right. So we'll say t is an upper bound for that. Okay. But in either case, it's an order 1 operation, right? Worst case, it does the if and the swap, but in neither case does it depend on n. Right? So there's an upper bound for how long that can take, and it doesn't depend on n. But that's a good observation. So the J loop costs me n minus 1 times t amount of time. Let's talk about the I loop. Oops, the I loop. So how much does one pass of the I loop cost me? N minus 1 times t. And how many times does that happen? Right, I equals 0 to n minus 2, or n minus 1 times. Okay. Now you do have to pay careful attention to indices and n. This summand in here, the thing underneath the summation sign, is independent of the index I, right? So what's it equal to?
Another n minus 1.
It's just n minus 1 times n minus 1t. Like that. Okay. Big O of big O of n squared.
Is that good?
We can do better.
Alright.
We can do better. Quick sort.
Maybe quick sort.
Yeah, we can do better.
What's a quick sort? Just curious.
Well, we're going to do it after break, but
It's big O.
oh, its big O is n log n, average runtime. Its worst case is still O n squared.
And that's already in the reverse.
I can't remember. I think worst case for quicksort is, yes, a reverse order list. But don't hold me to that. It's been a while since I've reviewed it. So worst case, quicksort is no better than bubble sort or anything else. But the worst case is extremely rare. And so on average, it's n log n. So what we've just shown is bubble sort is order n squared. Now, this is not the best version of bubble sort. What's an improvement that we could do to this bubble sort that I've written here that would make it a little bit better? Exactly. So every time I make a pass on the I loop, there's one guy in place, and it's where? It's at the tail end, right? So I can shorten the J loop by I and still have a sorted list. So let's see how that works.
What was that?
Clearly, Microsoft makes the best software in existence. I think that's what we should
Okay, so how can I tweak this? I can put a minus I right there. Let me erase that a little bit. So does everybody see that? We just, in fact, let me, I'll just sort of really emphasize this. What do you think? Is that going to change the order of this algorithm? Let's see. So we work from the inside out again, J loop. The inner loop, we're still doing T work each time through, right? Maximum of T work each time through. The difference is it only runs now from 0 up to n minus 1 minus I, which is how many times? It's just n minus I, right?
Yes.
Everybody okay with that? All right. So it's n minus I. The big difference here is in the previous example, it was just n minus 1 times t. Now it's n minus I times t. Let's see how badly that complicates our lives. Not very much. So we know that to do one complete J loop is going to cost us n minus I times t time. Now let's do the I loop. I loop. So how much work does it take to do a sweep of the I loop? One I loop run. It takes this long. And how many times do you do it? Yes, thank you.
Is that true of your bubble?
Yes, thank you. So it is, you were right, weren't you? Or I don't know if you were right, but yes, there's a typo there. And so there's a minus 1 there. It's not going to make a difference, but it's good to be correct. Okay. Everybody agree with that?
That's a higher sense.
Yes, it is. Let's propagate. Good. All right. Now that we've got all of our limits correct, some of this depends on I and some of it doesn't. So what we have to do is sort of do some algebra and separate out the bits that do and the bits that don't. So let's carry along this I equals 0 to n minus 2 for a little while. We have n times t minus I times t minus t underneath the summation, right? Now there are pieces of this that depend on I and pieces that don't. I'm going to separate or distribute the sum across, separate out the pieces that depend on I and those that don't. I'm going to just put a minus sign here, and a t here, and an I here.
Do we get to use the Schuler-Reed assignment?
Dude, yes we do.
Yeah.
It's going to be awesome. Okay, so what do we know here? These are just a string of equalities here. The first guy runs n minus 1 times, so we have n minus 1 times n minus 1 times t. So that's this bit. Starts at 0 though.
Oh.
So it runs n minus 1 times. Okay, the second bit might as well start that at I equals 1, right? And there's a formula, which I'll write off to the side, that some of you may be familiar with. Sum k equals, say, 1 to capital N of k is n plus 1, n times n plus 1 over 2. Right? Back down here in the problem that we're working on, I is k, or k is I, and capital N is n minus 2. So we make that substitution. And what we get is n minus 2, n minus 1 over 2. That's pleasant because we have now eliminated I. And it's simply a matter of convincing ourselves what order n this actually is, what big O of n this actually is. So we do still have to do a bit of algebra. So we do that, and one of the things that you have to be worried about, in particular when you're mixing positive and negative terms in one of these analyses, is that you don't get complete cancellation. Now, if you did get complete cancellation, in particular what I'm worried about is the highest order term. The highest order term here is n squared, right? And what's the highest order term here? Negative 1/2 n squared, right? Negative 1/2 n squared. And what we're left with as the highest order term in the whole expression is plus 1/2 n squared. We'd be concerned and we would know that we did some sort of algebra mistake. Not necessarily would we know it, but we would be a little bit worried if those top order terms canceled. Sometimes when you're doing analysis of algorithms, this beautiful, miraculous thing happens and the highest order terms do cancel. And what you've shown is that your algorithm is much better than you thought it was. It's a wonderful thing. But you do have to be really careful when those top order terms go away, because what you want to do is make sure that you're not feeding somebody a load of crap. And so you pay really close attention to those highest order terms. In this case, we see that the highest order term, we can multiply it out. N squared minus 2n plus 1 minus 1/2 n squared minus 3n plus 2. And if we then combine similar powers, we get 1/2 n squared. We get,
Sorry.
yes, 3/2 and negative 2. Is it what, negative n over 2 or negative 1/2 n? Not that I care about that term at all, but and then the last one actually cancels, so we're left with that. And now we can safely say that this is big O of n squared. So shortening that inner loop in terms of the order of the algorithm had no effect. It does save calculations, right? But it doesn't change sort of the intrinsic scaling of the algorithm. So it is worth doing, but it's not going to change the intrinsic nature of the algorithm. Yeah.
And this is assuming about the t. The t is a constant.
T is a constant. Yes.
Okay. And we just
So t, just to remind everybody, t is an upper bound for the cost of this single statement.
And we can see if it's that's a really cheap statement.
Well, I don't care how expensive it is. All I care about is what?
Oh, how many?
It doesn't depend on n. That's all I care about. Does everybody get that? Okay. There's actually one more efficiency that we can introduce to this bubble sort. Does anybody know what it is? No, it's not as complicated as that. There's just one more check that I can do to possibly shorten this thing.
If your list is fully sorted before you're done, you just
Exactly. So what we can do is introduce, let me see if I still have that guy in there.
The majority of cases, though, is that actually going to save efficiency?
It's not a really important thing to do.
That's the best case scenario.
What it's going to do is going to let me talk about 3 really important topics: best case, worst case, and average case. Right now, let's talk a little bit about, there's really nothing I can talk about with regards to those 3 ideas with the previous 2 algorithms. They're completely deterministic. No matter what the array is, they're going to run the same amount of time. This guy introduces a little bit of uncertainty. If the array is sorted sometime in the middle, stop. So let's talk about that. Where does that happen? So we're going to get a bool. And I think I just used the intelligently named done algorithm or Boolean, and then let me make some space. And I'll just put done. So every time I start the inner loop, I'm going to assume that the list is sorted. And let me make some more space here. I have to go kind of right here, don't I? So let's get these guys. And then let's get these guys. curly brace here, and a curly brace here, and in here I'm going to do done equals false. Does that make sense to everybody? So if I do a swap, then I'm not done. Let's go back to the simple guy, the one the one that wasn't shortened, since that's the one I had in my cut buffer. Doesn't really matter. And let's say that I have to run this thing from beginning to end. That's called worst case. And worst case is big O of n squared. We already showed that. That's what would happen if you just had to run it all the way to the end. What's best case? Best case is it's sorted, right? And you'll run through that inner loop once, and then you'll quit. And so Evan says n, and Evan is right. Order n. Right? Because how much work does it take to do one complete J loop? It takes order n to do one complete J loop. So best case is order n. Average case. This is actually often a hard thing to answer.
Just n squared plus n over 2.
I'll tell you what it is. It's order n squared, average. But what I'm going to talk about is what does average case actually mean. Here's the technical definition. Let Dn be the set of inputs to a program. Of size n. And let Ti be the running time of an input I. And let Pi be the probability of an input I. The average case running time. Actually, then maybe you can help me solve this guy. So the average running time, you'll not be surprised to learn, as a function of n, is just the sum over all possible inputs of size n, the probability of that input occurring times the time that it takes to occur. That's the technical definition.
Actually, it's just probably a mass function.
So then, like I said, maybe you can help me. I have a collection of integers. What's the probability of a particular input occurring? And how long does it take to sort that particular input? That's what's hard here. For example, let's say the list is already sorted. Let's say the list comes in and it's already sorted. What's the probability of that happening? Let's assume they're distinct. So a set of distinct integers?
1 over 8.
Yeah, 8 in this case, n in general, right? So the probability of getting a sorted list, there's one possibility, and so the total number of possibilities is n factorial, right? So 1 out of n factorial, so the probability is 1 over n factorial. How much work does it take to sort that list? What's the running time of that particular configuration? Big O is fine. It's actually big O of n, right?
Right.
The sorted one is big O of n. Okay. So that's about as much as I got done at my desk this morning. Where do you go from there, right? So you have to essentially come up with all the possibilities and how long it takes to run those possibilities. So the way I was headed, and like I said, I didn't finish this calculation, but let's just consider distinct guys, and let's say that n minus 1 of these guys are in order and one of them is out of order.
Don't you only care how far to the right the least element is?
How far to the right the least element is? I mean, sure.
Can't you describe all of your cases in terms of that? Because one swap through is going to move it 1 to the left. The next swap through is going to move it 1 to the left. So if the least element starts on the right, you have 8 swaps. Oh, although if it starts on the far left, then that doesn't incline anymore.
That's kind of what I'm worried about. And so the counting of this thing, and like I said, those of you that have had stats and have thought about this a little bit more than I have, maybe you'll have a better shot at this. Here's the way I was going. Let's say that you have n minus 1 of them are in place and one of them is out of place. So this guy's out of place. Well, where can it be out of place? It could be here or here or here or here or here. It could be anywhere between or at the head or at the rear, right? Except one of those places is actually the right place. Okay, so it can be out of place in n minus 1 ways. One guy can be out of place in n minus 1 ways. And how much work does it take to get it in place? Worst case, how much work does it take to get it in place? Order n. Order n, right? So that's kind of the way I was headed. So if one of these, this guy can be out of place in how many different ways? So one item out of place.
You can never have exactly one item out of place.
Well, the rest are sorted. So the rest on the set of 7 are in the right.
They're in the right order.
Okay.
Yeah, they're in the right order. And like I said, I may not be thinking about this in the right way. I'm just trying to sort of make it compatible with this bubble sort algorithm. So if one guy's out of place, there are n ways or n minus 1 ways it can be out of place. And if there's one guy out of place, how many sweeps does it take? It takes 1 sweep to get it into place. So then I thought, well, what if there's 2 out of place?
If there's one guy, it can take more than 1 sweep to get it. One guy out of place, it can totally take more than 1 sweep to put it back in place.
Yeah, you're right.
Right? 2, 4, 6, 8.
So I'm not thinking about this the right way.
Sweeps to
Yeah.
get the one back in place. I think you have to do it in terms of like how many spaces you need to move it, which is really hard.
Yeah.
Well, would there always be like one most out of place item that would define how long it takes?
No, right? Because that was the example that I was thinking of. But if you have
And it might be a problem if it's too high.
Doesn't the algorithm move every element 1 towards its proper position on any given sweep? If you could prove that, then you could prove that that's right. That the quality of the algorithm for sorting any given sequence it'll sweep for the number of times that the most out of place element is out of place, right?
If that's true, yeah.
Or you wouldn't have to show that it moved every element one. I should show that it moved the most out of place element one towards its proper place.
No, because then if it does that every time, then you still have other elements out of place, right?
But I don't think it's true that it moves everything.
Towards its proper place, I think.
Like, what if the element was too low, but then, like, what if the element was into, I guess, high rank of a place, but then the element right next to it was, like, I don't know.
And what if a guy is in place?
Yeah, you're right. So like 20,
Like-
19, 1.
The front of the list.
19 towards the front.
Yeah.
On that
Right.
first sweep.
I don't know. I'll think about it. Maybe I'll come back after break and have a nice solution, and maybe I'll just forget about it. So, but you can see how this leads to some interesting mathematical problems. And this again is abstract CS. This is what an abstract CS person would do. Would look at average run times. They turn into really complicated problems, as even a simple bubble sort shows.
Thank you. Oh.
Okay. And with that, I bid you good break.
Official.
Yeah, for me.